Hello and welcome to this next talk in the course on pattern recognition. We have been considering linear classifiers for the last so many lectures. Specifically, in the last few lectures, we have been looking at the linear least squares approach, both for classification and regression. Least squares approach minimizes sum of squares of errors, and we have seen how we can use that to learn linear models, and we will continue with that now. So, the least squares method is based on the criterion of minimizing mean squared error, and we have seen how we can derive linear least squares algorithms for classifiers, for learning regression functions, and we also looked at logistic regression for learning classifiers. Now, there is one other approach to learning linear classifiers, which we very briefly mentioned at the end of the last class, and that is the Fisher linear discriminant. Right? While least squares is also a good way of learning linear models and is a very standard way, Fisher linear discriminant actually somewhat predates the least squares approach. It is a very interesting approach to learning linear classifiers, and today we will be looking at Fisher linear discriminant as a method for constructing linear classifiers. Okay. Any linear discriminant function based classifier, essentially given a feature vector x, it decides that x belongs to class 1 if w transpose x plus w naught greater than 0 for some given w and w naught. If w transpose x plus w naught is greater than 0 is one class, less than 0 another class. That is what a linear classifier, linear discriminant function based classifier is about. Now, because w is a vector, we can take it as a direction in RD, the appropriate space. Then w transpose x is nothing but the projected value of x onto the direction w. So, if I think of this inequality as w transpose x greater than minus w naught, and if it is a good classifier, what it means is, if I take any x that belongs to class 1 and project it onto w, the projected value, namely w transpose x, is greater than minus w naught. On the other hand, if I take any x in class C0 and project it onto the direction w, then the projected value w transpose x is less than minus w naught. Right? So, essentially what a linear discriminant function is doing is looking for a direction w such that if I project the feature vectors onto that direction, then along the direction the two classes are well separated. On that direction there will be some threshold, in this case minus w naught, some point along that direction, so that the projected versions of all feature vectors of one class will be on one side of this threshold, whereas the projected versions of all the feature vectors of the other class will be on the other side of this threshold along the direction w. So, we can think of the best w for a linear classifier to be a direction along which the two classes are well separated. So, we are looking for a particular direction feature space such that if you project all the vectors onto that direction, all the feature vectors onto the direction, I get a very good separation between the feature vectors of the two classes. Okay. So, the idea is that we project the data along the direction w, and separation between points of different classes in the projected data is a good way to rate how good w is. So, now to learn a good w, I can take different w's, project the data onto these w's, and I am asking which w is there which will maximize the separation between the classes. Okay. This is the basic idea of Fisher linear discriminant. Before we go into the mathematical details, let us look at a simple example. Let us say this is the two class problem. Reds are one class and blues are another class. If I project all data, for example, onto the x axis, the reds and blues get intermingled on the x axis. Similarly, if I project it onto the y axis also, they get intermingled. But we can easily find a direction, namely this line. If I project the data along this line, as you can see, if I recode my two-dimensional feature vectors as one-dimensional feature vectors by projecting them along this direction, then all one class patterns are one side and all other class patterns are the other side. The actual separating hyperplane is perpendicular to this direction. So, if I think of W at this direction, obviously W is perpendicular is the normal to the separating hyperplane. So, that will be the separating hyperplane. So, I can think of finding the best W as finding a direction along which I have to project the data, so that the all feature vectors of one class in the projected space are well separated from the feature vectors of the other class. So, Fisher linear discriminant is a way of formalizing this notion of finding the best direction to project, so that the two classes get well separated. So, what does Fisher linear discriminant do? We want to find a direction W such that the training data of the two classes are well separated if projected onto this direction. So, to do this, of course, we have to find a way of formalizing this notion of what we mean by well separated. So, essentially we need to have a figure of merit, some number that I can assign to every W. So, I want some J of W which assigns a number to every W, a figure of merit, such that the number tells me how well projection onto that W will result in proper separation. Okay. So, we will do that, we will formalize this by first considering a two class case. Okay. So, let us get our notation right first. As we have been looking at, our data is always xi yi, this is the training data, we have n samples, xi are the feature vectors, they are in Rd, and yi is the class label. We are considering two class. So, let us assume yi is 0 and 1, and these two classes we will denote by C0 and C1. Okay. So, what it means is when yi is 0, then I can say xi belongs to C0, and when yi is 1, I can say xi belongs to C1. Okay. Let us say out of the n samples, n0 training samples are in class 0, that is C0, and n1 training samples are from class C1. Obviously, n is equal to n0 plus n1. For any given any W, let Zi denote W transpose Xi. So, Zi are the projected data along any direction W. Okay. So, Zi are the one dimensional data that we get after projection. Okay. This is our notation. Let us say M0 and M1 denote the means of the data from two classes. So, that is essentially the sample means. So, M0 is simply the mean of all Xi that are in class 0, and there are n0 of them. So, 1 by n0 summation xi belonging to C0 will give me the sample mean of the class 0 data vectors. Similarly, 1 by n1 summation xi belong to C1 gives me the sample mean of class 1. So, the corresponding means of the projected data would be what? If I project xi onto W, I get W transpose xi. So, if I take mean of W transpose xi, that will be same as W transpose M0. So, on the projected data, let us denote the mean by small m0. So, the mean small m0 will be W transpose capital M0 and small m1 will be W transpose capital M1. Okay. So, these are the means of the projected data when data is projected onto the direction W. So, if I want good separation, what I mean is the difference between M0 and M1 should be large. So, we can say M0 minus M1 or M1 minus M0, it really does not matter, gives us a good idea of the separation between the samples of the two classes when the data is projected onto the direction W. So, we can say a good direction W is one which maximizes this separation. So, we may want W that maximizes M0 minus M1 whole square, because that gives me large separation. But there are two caveats here. Just maximizing M0 minus M1 is not a good idea. Why? What is M0 minus M1? W transpose capital M0 minus W transpose capital M1 whole square. So, is W transpose capital M0 minus capital M1 whole square, right. So, just by scaling W, I can increase this difference, but that is meaningless. A scale factor, a positive scale factor makes no difference to the linear classifier. So, first we have to find some function that is scale independent, but more importantly, what is good separation depends on how much data spread is there. We are only looking at the distance between the means as we already seen when we considered Bayes classifier for normal class conditional densities. Essentially, the difference between the means relative to the variances is what tells us whether the class are well separated or not. So, to look at the distance between the means m0 minus m1 relative to the variances of the two classes. Okay. So, that is how we have to formulate our objective function for W. So, let us first calculate something that is like variance. Let us define S0 square to be W transpose xi minus m0 whole square. W transpose xi is the projected data, that is Zi. This is summation over xi belong to C0. For all xi in C0, the mean of the projected data is m0. So, W transpose xi minus m0 whole square summed over xi belong to C0 is like the variance of the projected data of class C0. I say like because I did not put 1 by n0, I could have put 1 by n0, but we did not. So, this is essentially just except for a multiplicative factor, constant multiplicative factor, this is essentially variance of the projected data from class C0. Similarly, if I define S1 square to be summation over xi belong to C1, W transpose xi minus m1 whole square, because m1 is the mean of the projected data of class 1, this is except for a multiplicative factor is the variance of the projected data in the for class 1. So, what we want is we want large separation between m0 and m1 relative to the variances. Okay. That is our objective. So, I can formulate this as a objective function for W as follows. So, we say we want to maximize J of W, where J of W is defined as m1 minus m0 whole square by s0 square plus s1 square. So, we want large separation m1 minus m0 whole square relative to the variances s0 square plus s1 square. By the way, even though this equation looks as if there is no W on the right hand side, you know all m0, m1, s0, s1 everything depends on W, right. S0 square, s1 square depend on W, my m0 depends on W. So, right. So, this is a function of W. So, we want to maximize the difference between the means in the projected space relative to the variances. Okay. This of course, is also scale independent, that is not really evident right now, but we will see it by rewriting this in a more convenient form. Okay. To rewrite this in a more convenient form, let us start with the numerator. What is m1 minus m0 whole square? M1 is W transpose capital M1 minus W transpose capital M0 whole square. This I can write as W transpose into m1 minus m0 the whole square. So, because W transpose m1 minus m0 is a vector, I can always write it as W transpose m1 minus m0 into m1 minus m0 transpose W, right. So, m1 minus m0 whole square can be written as W transpose m1 minus m0, m1 minus m0 transpose W. M1 is M1 and M0 are the means of the data. If data is an odd D, these are D vectors. Recall that our notation is all vectors are column vectors. So, M1 minus M0 is a D by 1 vector, M1 minus M0 transpose is a 1 by D vector. So, this is a matrix. Okay. So, this is often called the outer product matrix for between the two vectors. So, I can write M1 minus M0 whole square as W transpose some matrix into W, right. So, I can write m1 minus m0 whole square as W transpose, let us call that matrix S subscript B. So, W transpose SPW, where SB is m1 minus m0, m1 minus m0 transpose. As I said, this is a D by 1 vector, this is a 1 by D vector. So, this is a D by D matrix. Given any vector x, x transpose is called a outer product, and outer product is always a symmetric matrix. Also, I hope all of you remember that the outer product is a rank 1 matrix, because all columns are multiples of other columns. So, is a rank 1 matrix. So, such a matrix SB, this is a D by D matrix, because our feature vectors are on odd D. This matrix SB is often called between class scatter matrix. Okay. So, I can write m1 minus m0 whole square as a quadratic form involving the matrix SB, which is the between class scatter matrix, which is defined by this. In a similar way, I can write S0 square and S1 square also as quadratic forms. So, let us try to do that now. S0 square by definition is W transpose xi minus small m0 whole square. We know small m0 is W transpose capital M0. So, S0 square is W transpose xi minus W transpose M0 whole square summed over xi belonging to C0. So, I can rewrite this as W transpose into xi minus M0 whole square. Now, once again just like what we did for earlier, I can write what is inside this summation in terms of outer products. So, I can write this as W transpose xi minus M0 into xi minus M0 transpose W. Now, the summation is over xi. So, W can come out of the summation. So, if I pull W out of the summation, I get W transpose summation xi belonging to C0 xi minus M0 xi minus M0 transpose W. See, M0 is the mean of all xi in class 0. So, if I did this and divided by 1 by M0, if you remember, this is the maximum likelihood estimate for the covariance matrix. Right? This is the ML estimate for the covariance matrix of class 0. Right? So, I can write S0 square as W transpose xi belonging to C0 xi minus M0 xi minus M0 transpose W. This matrix of course is not at the covariance matrix, it is the covariance matrix except for a multiplicative factor, because I need 1 by N0 to make it an estimate of the covariance matrix. If I did the same thing for S1, the only difference will be the summation will be over C1 and M0 will become M1. So, similarly, S1 square will become W transpose the same matrix, but summation over C1 xi minus M1 xi minus M1 transpose W, which now means I can write S0 square plus S1 square as W transpose SW W, where SW is another symmetric matrix given by the sum of these two matrices x belonging to C0 xi minus M0 xi minus M0 transpose plus x belongs to C1 xi minus M1 xi minus M1 transpose. So, this this matrix, this SW, which is also a D by D matrix, is called within class scatter matrix. Essentially, the first term here is proportional to the covariance matrix of the first class of class C0, and second term is proportional to the covariance matrix of the class C1. By covariance matrix, we mean the sample mean estimate of the covariance matrix. Okay. So, SW is called the within class scatter matrix. So, we can write S0 square plus S1 square as a quadratic form on SW, M1 minus M0 whole square as the quadratic form on SB. So, now J of W becomes W transpose SPW by W transpose SWW, okay, is the ratio of two quadratic forms. Right. So, first thing to note, so basically this is the same J as earlier. So, we just rewritten it. Originally JW is M1 minus M0 whole square by S0 square plus S1 square, because both the numerator and denominator can be written as quadratic forms on some matrices, we written them like that. So, this is the J that we want to maximize. Now, it is very clear that is not affected by scaling. If W is replaced by KW, the K will cancel from both numerator and denominator. So, this W is not affected by this JW is not affected by scaling of W as it should be. And it is easy enough to calculate. Given the data, I know how to calculate SB, I know how to calculate SW. So, I can calculate both the matrices, and hence given any W, I can calculate JW. And in addition, this is a very nice optimization problem. Essentially, you want, given two matrices SB and SW, you want to find a vector capital W which maximizes the ratio of quadratic forms. Maximizing ratio of quadratic forms is a very standard optimization problem, and we can solve it generally easily enough. So, let us see how to do that. So, this is what we want to maximize. So, if we want to maximize, we differentiate or find the gradient and equate to 0. So, if I differentiate with respect to W and equate to 0, what will I get? I can first do 1 by W transpose SWW into derivative of the numerator, that will give me 2 times SPW, plus the numerator W transpose SPW into derivative of 1 by W transpose SWW. I can write it as minus 1 by W transpose SWW whole square into the derivative of this SW, which is 2 SWW. Right. So, just by differentiating this and equating to 0, I get this. In this, this is a quadratic form, this denominator. So, is a scalar, this is a quadratic form, that is a scalar, this is a quadratic form, that is a scalar. So, I have one vector here SPW, another vector here SWW. So, it is some constant into the vector SPW minus some constant to the vector SWW is equal to 0. That means, this vector and this vector are in the same direction, because constant times 1 is the other. So, what this implies is that the vector SPW is in the same direction as the vector SW. So, the W that maximizes J is such that the matrix SB times W is a vector in the same direction as the matrix SW times W. Okay. Thus, any maximizer of J has to satisfy SWW is some constant times SPW, okay, where lambda is the constant. This is reminiscent of the eigenvalue problem, right. An eigenvalue problem, you get Ax is equal to lambda x. So, some matrix into a vector is lambda times the same vector. Here I am not getting the same vector, but some other matrix multiplied W, but this is also very similar to the eigenvalue problem. So, this is known as the generalized eigenvalue problem. There are standard ways of solving generalized eigenvalue problem. There are methods based on LU decomposition and so on. So, once we know it is a generalized eigenvalue problem, for example, your MATLAB will have a very standard routine for solving this. But anyway, we will not get into the details of special methods to solve generalized eigenvalue problem, because often we can solve it easily. But right now, we note that because the generalized eigenvalue problem, by solving the generalized eigenvalue problem, we can always find the best direction W. Okay. But as I said, often I may not have to solve the generalized eigenvalue problem. This is because the real symmetric matrix SW is often invertible, right. Why is that so? SW is this matrix, okay. Xi minus M0, Xi minus M0 transpose, summed over Xi belong to C0, Xi minus M1, Xi minus M1 transpose, summed over Xi belong to C1. There are at least two reasons why we can suspect that this matrix is invertible. One is, we know for each I, Xi minus M0 into Xi minus M0 transpose and outer product is a rank 1 matrix. So, this adds a lot of rank 1 matrices. When you add rank 1 matrices, suppose I add x2 minus M0 into x2 minus M0 transpose to x1 minus M0 into x1 minus M0 transpose. If x1 and x2 are linearly independent, then this becomes a rank 2 matrix. So, if I keep adding many rank 1 matrices, of course, the rank can at most go up by 1, but if we assume there are sufficiently many, so the first reason is that this is the sum of a large number of rank 1 matrices. If the number is large and xi's are in general position, it is unlikely that all the xi will be in some lower dimensional subspace. Since if all the xi are not in some lower dimensional subspace, then adding all these rank 1 matrices should give me a full rank matrix. Normally, the number of samples is much larger than the dimension D, and hence adding that many rank 1 matrices should give me a full rank matrix. Another reason why we think why often this is invertible is that, as you have seen, each term in this is a good estimate, especially if the data is large, of or proportional to a good estimate of the covariance matrix, and the covariance matrix will be invertible. Right. So, by both ways we expect SW to be invertible. Suppose SW is invertible, then it is much easier to solve for the, let us say SW is invertible. So, we have seen the W has to satisfy SW into W is equal to lambda SBW. So, if this matrix is invertible, I can multiply by SW inverse. So, I get an equation for W, right, or at least a relation W is equal to something. So, let us look at that relation. Suppose SW is invertible, then W can be written as SW inverse SP times W. There has to be a lambda here. I omitted the lambda because ultimately constant factors do not make much difference, but anyway there is a lambda here. Let us not worry about that right now. This looks like, of course, an eigenvalue problem. Putting a lambda here it is the eigenvalue of SW inverse SP, but we do not even have to look at the eigenvalues, because SBW, what is SB? M1 minus M0, M1 minus M0 transpose into W. We know M1 minus M0 transpose W is nothing but little m1 minus little m0, which is scalar. So, this is some scalar k times m1 minus m0, as I wrote here, k is equal to m1 minus little m1 minus m0. So, SBW is a vector that is proportional to m1 minus m0. So, I can replace SBW by some constant times m1 minus m0. So, which gives me W is SW inverse m1 minus m0. There are so many constants, there is a lambda here, there is a k here. So, ultimately there will be some constant times SW inverse m1 minus m0, but as I said, constants do not make any difference in a linear classifier, right. We can accordingly scale W on B to anything that we want. So, essentially we can find the W except for a scale factor to SW inverse m1 minus m0, and I do not have to worry about the scale factor. I can take this to be W, because I am in a linear classifier context. So, this is the W that I can use as the Fisher linear discriminant if the matrix SW turns out to be invertible, okay, which as we just now said, very often that would be the case. So, let us sum up how we obtain Fisher linear discriminant. We are given data. Given the data, we first form the scatter matrix SW and also calculate the means M0 and M1. Right. Once the within class scatter matrix SW is invertible, I can directly find W. If SW is invertible, you can calculate W by SW inverse M1 minus M0. Right. That is the Fisher linear discriminant direction, or it is the normal to the hyperplane classifier given by the Fisher linear discriminant. Just for completeness, let us remember that even if SW is not invertible, there are techniques to find maximizer JW by solving some generalized eigenvalue problem. Okay. There are some techniques, even the generalized eigenvalue problem, if SW is not invertible, there are some issues. Just so that you will appreciate that there are some issues, let me just go back to if SW is rank deficient, what it would mean is there can be some W at which W transpose at W can go to 0, right. Thus, there would be some W for which this will be infinite, but that is not the W we want. So, we have to define this a little more carefully, okay. But it does not matter, there are techniques to take care of it. So, we will not go there, but we will just remember that if SW is invertible, W is given by this. Even otherwise, one can find a maximizer by solving some generalized eigenvalue problem. Okay. So, that is how we obtain the best direction W, right. Very often this is what is given as the Fisher linear discriminant. As I said, in most pattern recognition problems, SW would be invertible. So, this is the Fisher linear discriminant. Okay. But obviously, we have found only the best direction W. We have not yet found a classifier, right. Let us remember that a discriminant based classifier is sin of W transpose x plus B. So, I have to find the B also, right. All that we have done so far is how to find the best W, but after having found best W, to convert it into a classifier, I still have to find a B. But this is a much simpler problem, right. We have to still learn the best B, but the simple problem of just learning a threshold. We are saying this is the best direction. So, now we have one dimensional data, I want the best threshold. So, now given one dimensional data on class labels, I just want a threshold based classifier, I am asking which threshold is good. There are many methods. For example, we considered ROC, how we can experimentally calculate ROC and come to a threshold. That is one thing we can do. We can do any that kind of search for a threshold. We essentially have to, along W, we keep putting the threshold at various points, right, and keep asking, is my accuracy on the training data improving. I need only one threshold. So, I will start from some end of some point and keep moving, just is like a line search in any optimization problem. So, we can do a simple line search to find the best threshold, right, to maximize the probability of correct classification on the training data. Or what we can do is the projected one dimensional data Zi, that is what we have with class labels, we can simply take it as a one dimensional pattern recognition problem, and it is very easy to solve one dimensional pattern recognition problem. For example, we can take the class conditional densities to be normal, estimate the associated normal densities, very easy to do for one dimensions as you have seen, and then take the base classifier based on the estimated densities. Okay. This is also often done. So, in whichever way we do, that gives us the final Fechel linear discriminant. Okay. So, this is how I would obtain the Fechel linear discriminant. Okay. Fechel linear discriminant is also a popular classifier, just like the least squares. Now, the way we derive the Fechel linear discriminant, it looks quite different from the least squares method. As I told you, Fechel linear discriminant came from a also came from statistics, but not it came from a different direction. So, essentially linear least squares and Fechel linear discriminant evolved historically as different algorithms. Okay. However different it may look, there are close connections. As a matter of fact, we can think of Fechel linear discriminant as a special case of linear least squares. The reason we did not start there is that because historically it is important, it is very often used in applications, and it is nice to know another way of formulating what is a good linear classifier. But having said all that, one can actually mathematically show the equivalence of linear least squares and Fechel discriminant in a very specialized sense. What is specialized sense? Is the following. We start with some data xi, yi, this is our given data, xi is an RD, yi is 0, 1, this is our classification data. Given this data, suppose we form some new training data where xi's are same, but yi's are changed to yi prime. How do I form the new yi primes? Originally yi's are 0 and 1. So, if yi is 0, that is xi is coming from class 0, I take yi prime to be n by n 0. So, I am just changing the targets. For all class 0 patterns, the correct value to predict is n by n 0, where n is the total number of samples and n 0 is the samples of class 0. On the other hand, if yi happen to be 1, I take yi prime to be minus n by n 1. So, now I have got new data xi yi prime, where yi prime takes some real numbers, okay, not 0 ones, because n by n 0 and minus n by n 1 are some real numbers. Even though it takes only 2 real numbers, we will think of yi prime as some generic real number. Then we can treat this xi yi prime data as a regression problem, right. Xi's are an RD, yi prime are an R. I want a predictor. I want a linear predictor, y hat is W transpose x plus b. Simply viewing xi yi as some data for a regression problem, I can certainly use least squares to find a linear predictor, y hat is W transpose x plus b, using our standard linear least squares method that we have done in the last couple of lectures. One can show algebraically, the algebra is a little tedious, but it is there in one of your prescribed textbooks, namely Bishop's book, but it can be shown through somewhat long variant algebra, that if I had done that, if I take this data, recode it as xi yi prime and then think of this as data for a regression problem and then find a linear regressor, then one can show that the least square solution W that I obtain for fitting this model to this changed data will be exactly same as the W that we get out of Fechel linear discriminant, right. I am not proved this, I am not proving this, as I said the algebra is tedious and it possibly does not add much to go through the full algebra, is also there in Bishop's book, but you should know that it can be shown that the least square solution I obtain here would be same as the Fechel linear discriminant. Thus, one can show, one can see that Fechel linear discriminant can be viewed as the special case of linear least squares. So, it is not really different from linear least squares, but all the same it gives you another very important and useful idea of how one looks at what is a good linear classifier. Okay. There are other ways of looking at how good Fechel linear discriminant is. For example, we will take a simplest 2 class problem. Let us say we have a 2 class problem with both the class conditional densities to be normal, and let us say they have the same covariance matrix. Why same covariance matrix? If the 2 classes are the same covariance matrix, we know that the base optimal classifier is a linear classifier, right. So, now one can ask, will facial linear discriminant give me the optimal linear classifier, because facial linear discriminant can give me only linear classifiers. We can only ask whether it will give the optimal classifier when the optimal classifier itself is linear. So, let us take a case, class conditional densities are normal with same covariance matrix, when we know that the base optimal is a linear classifier, and we will show that facial linear discriminant will give me the same classifier as the base classifier. So, let us say mu 0 and mu 1 are the two means of the classes, and because the covariance matrix is same, there is only one sigma for both classes. The sigma is the common covariance matrix. Suppose given this data, if we want to actually implement base classifier, we would estimate the class conditional densities, let us say using Maxwell likelihood method. If we do Maxwell likelihood method, we know mu 0 and mu 1 will be estimated using sample means. Similarly, a similar sample mean estimator exists for the covariance matrix. So, then we know that m 0 and m 1 would be the sample mean estimators for mu 0. That is how we obtain m 0 is 1 by m 0 1 by n 0 summation x i. So, there is sample mean estimator for mu 0, similarly m 1. So, I would have obtained the same m 0 m 1 as the sample mean estimators for mu 0 and mu 1 had I tried to do this estimation of class conditional densities under Maxwell likelihood. Similarly, I would have got some sigma hat as the estimate for the covariance matrix. Okay. Then what will be the base classifier we implemented with these estimated quantities? If you still remember the base classifier that we derived for common covariance matrix case, it is a linear classifier W transpose x plus B, where the W is given by sigma inverse mu 1 minus mu 0. So, what I would have implemented sigma hat inverse m 1 minus m 0. Right. Now, we know that this has to be same as FLD, because we know that SW inverse that comes there is like covariance matrix. So, very quickly we will show that this W would be same as the W given by the facial linear discriminant. Coming back, this is the SW matrix. Because both classes are have the same covariance matrix, I could estimate the covariance matrix either from class 1 or from class 0. So, if I estimate this from class 0, that estimate would be proportional to this except for a proportionality constant. Similarly, if I estimate it from class 1, it would be proportional to this except for proportionality constant. Since the classes are the same covariance matrix, each of the two terms above would be proportional to the same sample mean estimator, right. So, the first term will be some A times sigma hat and the second term will be some B times sigma hat. So, essentially SW will be proportional to sigma hat, right. So, since SW will be proportional to the sample mean estimator for sigma, okay, we know that the facial linear discriminant, which is given by SW inverse m 1 minus m 0, is same as the base optimal classifier. So, facial linear discriminant is an interesting classifier, because at least in this kind of cases it gives you the base optimal classifier. So, it has a very interesting geometric interpretation, namely finding a direction along which classes are well separated. That's in itself is a nice interesting geometric interpretation. In addition, as we seen, it can be viewed as a special case of least squares, and also in the cases where base optimal is linear, I am getting, at least in the normal class conditional densities case, facial linear discriminant gives me the same classifier as the base optimal. Okay. So, that is the story of facial linear discriminant. Okay. So, to move on, we have considered various methods of learning linear classifiers and linear regression models, starting with perceptron, and then we spent a lot of time on linear least squares methods and now facial linear discriminant. But most of the time we are restricted ourselves when we are doing regression, we are talking of targets being in R. In the regression case, we assume the training data is xi yi, where yi belongs to R. What it means is we are only estimating real valued functions. So, one generalization that we may want to do is to generalize this to vector valued functions, right. Similarly, whenever we consider classifiers, in the classification problem we always restrict ourselves to two class problems. So, we have to generalize this to multi class problem. These are the two issues still left. So, this class will at least look at the issues involved, and will tell you what the things are, and pretty much that's all there is for multi-class classifier. We may just briefly touch upon it next class and leave it at that. Okay. So, let us do it one by one. So, let us first look at the regression problem. First consider estimating vector valued functions. Okay. What does vector valued function mean? Now, my training data is given by xi yi. As earlier, xi is a feature vector and it belongs is an RD, yi is the target. Now, because I am learning vector value function, let us say the function maps from RD to RM. So, yi will be M vector. I am sorry, this should not be RD, this should be RM. I am sorry about that, but anyway, y is a M vector. So, because we already put I for denoting the ith sample, let us denote the components of yi by yi1, yi2 up to yim. So, the main difference in the vector value case is that yi is now a vector of some m components for some arbitrary value of m. Okay. So, given any x, we want a model that can predict the target, which is a m vector. So, given an x, we want to predict y, which is actually an m vector given whose components are y1 to ym, and we want to do it using our basic linear methods. So, what it means is that we want to learn m w's and b's such that the jth component can be predicted as some affine function, that is w j transpose x plus b j. So, essentially the problem boils down to find m vectors w j and m scalars b j, so that my is a good model. My prediction model would be the estimate of the jth component in the target y hat j is w j transpose x plus b j. Right. What does that mean? If I just take this data and split it into many datas, xi yi1 is one data set, xi yi2 is another data set, xi yi3 is another data set, so on. For each data set, I find a standard linear least squares method, right. So, this learning a vector valued function is no different from simply solving m number of linear least squares regression problems. So, simply by running m linear least squares regression problems, we can solve the vector case. Of course, we can all put it into a better formalism. We can actually put all these wj's as columns of a w matrix and write the entire least square solution in a vector matrix notation. But except for some complication of notation, there is nothing really conceptually novel here, because we are simply effectively running m number of linear least squares regression problems. Okay. So, which means in principle we know how to solve the linear model problem, even if we have to learn a target function which is vector valued. Okay. Now, let us come to the multi-class problem. If I know how, so far we know many methods for learning two class problems. So, if I know how to learn two class problems, can I use them to learn multi-class problem? The issue is just a little more complicated here. We have earlier considered this. So, let us say we have k classes C1, C2, Ck. Okay. So, we will come to decide how the data will be, but for now let us assume that we get xi yi, then yi takes any value between 1 and k. Note that earlier we always been looking at our classes some C0, C1, so on. This time we look at C1, C2, Ck. Okay. Now, as I said some time ago, essentially two class problem is the more fundamental problem, because we can solve multi-class problems simply by if you know how to solve two class problems. So, we can in principle solve a number of two class problems to solve a multi-class problem. There are at least two very generic techniques of learning a multi-class problem using two class methods. Okay. One is that I can learn k two class classifiers, where k is the number of classes, as follows. I learn Ci versus not Ci. So, the ith classifier I learn is learning to classify Ci versus not Ci. What do you mean by Ci versus not Ci? I have the data, training data of the K class case. So, I take all the data, all the Xi that belong to a particular class, say Ci, or say all data that belongs to C1 as one class, all the rest of the data as another class, right. Then I solve a 2 class problem whose objective is to say, given an X, is it in C1 or is not in C1, right. Similarly, is it in C2 or not in C2. So, I learn K number of 2 class classifiers. Each classifier is learning to distinguish between Ci or not Ci. This approach is often called one versus rest, and is a very standard approach in learning multi-class case. Okay. Especially when one does nonlinear classifiers, very often one goes for one versus rest approach. Another way of doing it is, instead of learning K, I learn KC2 number of 2 class classifiers. Now, for every distinct pair I and j, I am learning one classifier to distinguish Ci from Cj. The main, of course, I am learning more number of classifiers here. Why should I learn more number of classifiers? Why can't I use the previous method where I have to learn only K classes? One problem with the Ci versus not Ci learning could be that for this problem, the effective training set could be very skewed. Let us say I have 100 classes and I have, let us say 50 examples of each class, making a total of 5000 examples. Now, when I want to do C1 versus not C1, I have only 50 examples of C1, whereas 4950 examples of not C1. Right? Then, if one of the classes has much less representation in the training set than the other, in a 2 class problem, predominantly all training data belong to one class, then it is very difficult to learn the classifier. For example, in this case, if I have 50 of one class and 5000 minus 50 of the other class, then a classifier that always says not C1 has only a error rate of 50 by 5000 on the training data, which is very small, right. So, stupid classifiers can have very low error on the training set, and that always makes it difficult. Often what one does is, when one class has too many samples, then you resample from that. So, out of this 4950, maybe I take some 50 or 100 randomly selected samples and use that to do Ci versus not Ci. But when I do that, maybe that does not represent all the other not C1 classes. So, if the number of classes is very large, then one versus rest can sometimes be difficult, because the training data will be very skewed for the resulting 2 class problem. If I have only 3 or 4 classes, then it may not be so bad. But if I have 100 or 200 100 classes or 50 classes, then learning Ci versus not Ci could be a skewed data set problem, and I have to properly balance the data set. Okay. It is in those cases that learning Ci versus Cj classifier is good, because if essentially when I have got K class problem and I have training data, one expects that all classes are represented about equal measure. So, for a 2 class problem Ci versus Cj, I will have roughly equal number of examples for both classes. There is no skewed training set distribution. So, this is a little more easier, is more stable 2 class classifier learning, and that is the reason, even though I am learning more number of classifiers, I may want to do this. So, these are essentially the 2 ways of using, there are others, but these are the 2 main ways of using an algorithm that can learn a 2 class classifier to classify K classes. But however, there are issues with both of these, right. We'll look at some problem. That is not to say that these are not followed, but there are pitfalls with both the approaches, in as much as any set of such classifiers, this set of K classifiers or this set of K into K minus 1 by 2 classifiers, do not make a perfect a well defined classifier. Perfect is a wrong word to use, because you are not saying it has to have 0 error or anything like that, but at least it should be a well defined classifier. What do you mean by a classifier? Is a black box to which if I give an x, there is no doubt in the classifier's mind as to what class x should be going, because it is an algorithm, right? It has to be an algorithm. Whether it is right or wrong is a different issue, but for something to be called a classifier, at least structurally, given an x, it should be assigned to one unique class. But if I learn this many 2 class classifiers or this many 2 class classifiers together, they do not really define a proper classifier in this sense. Okay, that's what we will see next, that neither these approaches are really satisfactory for generalizing the linear discriminant function to multiple classes. Okay. So, before I will show you some examples of why this happens and tell you how we can solve this. But before I go there, I spent a lot of time telling you about these 2 ways of dealing with multi-class problems, because in spite of the problems I am going to tell you, sometimes people use this approach for solving multi-class problem, but we should still know what the pitfalls in the approach are. Okay. So, let us first consider one versus test approach. The problem is that there are regions of feature space where the classification is ambiguous, right. Let us say this is the linear classifier that separates class C1 on one side, not C1 on the other side. Let us say this is a linear classifier that separates class C2 on one side and not C2 on other side. Okay. And this is the region 3 where it is class 3, as it should be not C1 not C2. But there will be region like this where this classifier will say C1 and that classifier will say C2. Maybe my third classifier may say not C3, that is all right, but what should I do here? Because if I take any x here, one classifier says C1, other classifier says C2, my third classifier says not C3. So, that is okay, not C3 is fine, but is it C1 or C2? I have no way of knowing. So, this does not even define a proper function that maps every feature vector to a class label, right. The same thing is true even if we use Ci versus Cj approach. Once again, here is an example. So, in a 3 class case, so this is a C1 versus C2 line, right. That is a C1 versus C3 line. This is the C2 versus C3 line. In the center triangle where I put the question marks, if I take any x, one classifier will say C1, another classifier will say C2, the third classifier will say C3. Perfect disagreement between the 3 classifiers. What should I assign it as the class label? So, there is always this issue when I have that many 2 class classifiers. If the responses given by them are consistent, then given any x, I can decide on the class label for that x. But there will always be regions in the feature space like this, where the responses are inconsistent and one does not have any simple solution of how to put together all those responses into a proper class label. Okay. This is the problem of generalizing to multiple classes. Of course, there is a better way of formulating this. We have seen this when we considered multi-class base classification for minimizing risk. The same thing is true in the linear exponential functions. Essentially, the way to generalize to multiple classes is we will have k functions. I represent them as g subscript s as going from 1 to k, and each function is a standard linear function, that is affine function rather. Gs of x is w s transpose x plus bs, right. Now, I define a way of making this into a classifier all such functions as, now once I have all these functions, if you give me an x, I will assign x to class Cj if Gj of x is greater than Gs of x for all s. Right. So, I calculate the value of x at each of these functions, and whichever function has the maximum value of x at that point x, I will assign x to that class, because this is not at complete, because there will be ties, right. So, there might be say g1x and g2x might have the same value, and that is bigger than the value of gjx for all other j. Now, should I put x in class 1 or class 2? But once we come this far, we can have a very simple and arbitrary rule for breaking ties. For example, I can say that if the maximum is attained at more than 1 j, then I will put it to the j, to the least j. So, if g1x and g2x are the two maximum function values for x, then I will put it in 1, right. So, I can have any arbitrary but fixed rule for breaking ties, so that it becomes a proper function. Given any x, it uniquely defines a class label. So, essentially this is how one would like to generalize linear discriminant functions to multiple classes. Recall that this is the way we generalize the base classifier. So, now to learn a linear classifier for k class case, we need to learn all the k functions GS. The best way to do this is to use our vector valued idea of regression functions. So, what we do is we make the class label to be a vector of k components. What does that mean? If xi belongs to Cj, then in the training data the class label yi, instead of simply taking value j, it actually will be a k vector with the jth component 1 and all others 0. So, yi will be a k vector now, and to denote jth class j, I put 1 in the jth component and 0 everywhere. So, each yi will be a unit one of the coordinate vectors. So, we seen similar coding when we considered a discrete random variable as an ML estimation. So, the same coding we can use, we make the class labels k vectors. Now, learning k functions is same as a linear regression with vector value targets. I am given xi, yi are vectors, I want to learn a linear function. So, I can learn k functions using linear regression with vector value targets. So, this is one standard way in which linear experiment analysis can be extended to multiple classes. There are of course, some slightly different ways, and this by itself does not tell you how I can generalize logistic regression or special linear discriminant, because the structure of learning is slightly different there, but similar ideas can be used for generalizing logistic regression and special linear discriminant also. So, with the next class, we will just briefly look at how to generalize logistic regression to k classes, and then we will step back. We have seen some algorithms now for learning classifiers. We will just take a look at all the algorithms and then take a step back and ask, is there some theoretical ways in which we can say whether one classifier is good or not good? How do we decide whether a classifier is optimal or good, or is there a statistical way of defining the goal of learning in learning a classifier? So, we will do a bit of statistical learning theory, and then we return to learning nonlinear classifiers. Now, that we finished all linear classifiers, we will step back, do some statistical learning theory, and then come back and do the nonlinear classifiers. Thank you.